Ladies and gentlemen, please welcome a representative from Machina Labs.
Well, hello everyone. Is the audio okay? Can everybody hear me? Okay, cool. So my name is Ed. I spent most of my career at intersection of AI, manufacturing, and robotics. Work with teams to build rockets and launch vehicles, build teams to build robotic systems specifically for manufacturing. But more recently, I have been kind of more obsessed with this idea of overmatch. We talk a lot about weapon systems and defense systems that we need to build overmatch. And I think, but at core, we need something even more fundamental. We need new manufacturing capability that is completely rethought, that allows us to build these weapon systems. And in this talk, I'm going to talk a little bit about that. So we all, recently we all talk about the Golden Dome. Obviously, very ambitious project. Lots of money has been earmarked for it. I know a lot of you guys in DC have been working on it. It's a great policy challenge. I think up to this point, we have around like maybe $50 billion in kind of earmarked for it. The total budget seems to look like closer to $200 billion. But I think there's more fundamental challenge than just the money and the policy. In order to build some of the components we need for Golden Dome, we need new type of material. We need, for example, for Golden Dome, we need hypersonic gliders, hypersonic interceptors, and those are built out of materials that are traditionally very hard to process. Think of nickel-based alloys, titanium, and traditional manufacturing cannot really process those efficiently and economically. Now, on top of that, we don't really even have an industrial base to build them. So not only traditional manufacturing cannot process in them, but even in a traditional sense, we don't really have an industrial base that can process any type of the material. And the problem with the traditional industrial base, even if we had it, is that it is very inflexible, right? The picture you see is actually from an automotive plant. Today, if you want to build a product, a physical hardware product, you pretty much have to build a factory for it. Elon Musk famously said that the actual product is not what comes out of the factory, it's actually the factory, because the factory is very much specifically built for every hardware product you're trying to build. Those blue things you see on that shop floor, they are molds and dies that are used to build automotive panels. Each of them can cost up to a few $1 million to build and months of lead time. And each of those molds are very specific for the one part. The moment you want to change the material, you want to change the part, you have to build another mold. So traditional manufacturing is very slow, takes a long time to bootstrap, which means it significantly affects our ability to build new capability, especially on the defense side. Now, you might say, well, China is using traditional manufacturing technologies, and they're being pretty rapid and agile about it. They specifically showed recently on how fast they were able to basically surpass all automotive exporters, go past Japan in a matter of 4 years, right, in EV. But China have had decades now of building industrial base, right? The industrial base that we used to have when we outsourced it, but now China had that 10, 20, 30, 40 years of advantage on building an industrial base that can stand on top of it now, and with government support, in a matter of 4 years, take over the EV market in terms of exports, right? So now we have two options. We can either spend the same amount of time, or maybe a little bit faster if you have the gusto, to build this industrial base, or try to leapfrog it. Try to go to the next generation of manufacturing floors. And I really want to talk about that next option. This is the factory that we're envisioning would be the next generation of shop floors. Instead of being filled with geometry-specific, part-specific, material-specific equipment, it's filled with robots that are smart. These robots can do different types of manufacturing operations, can pick up different tools, apply it differently to material to do all kinds of different types of operations, build different types of products. and they're completely flexible, right? In the morning, they can be building automotive components. In the afternoon, they can be working on aerospace or defense articles. The core unit of this manufacturing plant is what we are building at Machina Labs. We call it Robo Craftsman. It's a robotic system that can do different types of manufacturing operations. As you can see here, it's forming a part without the need for any physical tooling or hardware. It is actually forming sheet metal part the same way a master sheet shaper deforms a sheet of metal into shape. Doesn't require any tooling. The same way a potter, another analogy would be the same way a potter deforms a clay bowl into shape. But right after that, it can pick up another tool autonomously, scan, create QC report, then pick up another tool that determines that it's the next step of the operation, in this case trimming, and do the trimming operation. This product is already deployed at the United States, the Department of Defense's depots, maintenance depots, to be used for aircraft maintenance. Now, the real enabler, as you see, the robots that you saw, you have seen it in other manufacturing plants. So the real enabler is actually the intelligence that drives the robots, right? Those robots, as opposed to traditional plants, they are actually very flexible and intelligent. They respond to the sensors and change their operation. There's a software stack that turns the design and uses artificial intelligence to turn it into a set of operations that the robot can do to form an accurate part. Not only it will create those instructions to form an accurate part, but it also gets the responses from the sensors, from how the material is reacting to the operation, to constantly update its models to do its operation better, but also learns new operations. You saw in the previous video, we were doing forming, we were doing trimming, but as we're gathering more data, we can teach it new operations. It can do forging, we can do heat treatment. There are other operations that we're constantly adding to it. Like a true craftsman, it can actually learn to do different operations. On top of all of this, because we are gathering a lot of data from the shop floor, we can do also global optimizations now, right? We can figure out, okay, how can we improve the power consumption of the factory? How can we improve the material consumption, right? It's now becoming this holistic stack that starts from start to the end of the process, and everything is digitized, and we have the data from a start to an end that allows us to do both local improvement in the operation, but also global improvements on the operations. Now, we talked a lot about flexibility and agility and ability to learn new processes. But the fact that through these robots we have more control over manipulation of the material and the process of the material allows us to actually start operating on those hard to form, hard to process material that I told you that we need for hypersonics and we need for Golden Dome. So alloys like titanium, alloys like nickel-based alloys, niobium-based alloys that are used for high temperature application, because these hypersonic vehicles that go at very high speeds, it generates a lot of heat. So traditional aluminum or steel is not a good fit for them. We can actually process those high temperature alloys much more economically, that with traditional manufacturing is either uneconomical or infeasible. Now, all of the stuff that I told you, I showed you a lot of renderings, but it's actually happening in reality. It's an online factory, right? We have 2 facilities right now in Los Angeles, a total of 110,000 square foot, that not only does defense products, but it also does commercial products. You're actually going to see in the video, we're manufacturing a new car door for our commercial customer in automotive space. So this not only allows you to be more agile and flexible on the defense side, but allows you to have factories that are dual use. In the peacetime, they can do automotive work, they can do marine work, and in the time of conflict, through just changing the software, you can put more capacity toward missiles and aircrafts. But the nice thing is that for the first time, because we're applying this to the commercial industry, we're able to also come up with applications that didn't exist. For example, this automotive customer is working with us to enable a new product category where you can go to a website and actually design and build a vehicle that is specific to you. You can design what hood you want, what fender you want, what tailgate you want, and get it at the mass producible prices, but get serial number of 1 out of 1 specifically designed and made for you, right? And then we also thought about, okay, you're building a very robotic system that's flexible, can do different types of material, different types of applications. But we wanted to also make sure that it's easily deployable. So it can actually bring up a facility really fast. This requirement initially came out of Department of Defense, where they wanted to not only do maintenance in the depots, but also be able to do it in the front lines. If we enter a conflict, let's say in Pacific, how long does it take for us to set up a facility to repair military systems? That was a huge concern for them. So we made this system so that it is actually portable. The whole system that you saw, like a transformer, it folds into 2 containers. These are ISO compliant containers that can be shipped using traditional methods. It can be put on a ship, it can be put on a truck, and can be deployed anywhere. Once it arrives in the destination, it doesn't require much facility requirements. You can put it on any warehouse floor as long as you have power to it. It unfolds and it calibrates itself, and it starts forming parts in the same day. You can see actually the cells in its container form on the bottom right corner of the screen. So thank you so much for listening to me and spending time here. We think really for us to develop Overmatch, we don't need to just develop new weapons and defense systems. We really need to rethink how we build them, especially these new weapon systems that require a lot of trial, a lot of development, requires manufacturing technologies that are flexible and allow us to do those trials, do different types of parts, different types of materials. I don't know if you have time for Q&A, but good? Okay, cool.
So it looks like you're creating an equivalent of a robotic or machine agent so that it's both the smart and the physical, and you can orchestrate any number of opportunities or configurations on the shop floor. Would you think that's a good analogy?
Yes, no, absolutely. I think good analogy to kind of complement what you said is, in the world of digital world, we used to have supercomputers. I would equate supercomputers to current factories. You know, we had one computer that can build one thing or do one type of computation over and over again, right? But it was very expensive to build. It was this giant supercomputer that maybe could do like astrophysics calculations, right? And for the most part, we dropped that paradigm for the paradigm of data centers, where we have a collection of small computers that are each of them are programmable, and collectively they can be as powerful as a supercomputer, but now you can program them to do astrophysics computation one day, and then do host web services another day, do ML work and AI work another day. We're trying to do the same paradigm for manufacturing. Once you have a facility that you fill it with these units of manufacturing, we call it Robo Craftsman, then you can program this facility to do different types of operations just through changing the software. And through horizontal scaling, you still get the throughput that you need from a large factory. Correct.
Thanks, really appreciate the comments. This looks fantastic, but it still looks like it's still going to be, like if you're doing a mass production of 100,000 items, you'd probably still want to do the more traditional thing, I would think. Where is that break point where, like, how many would you need to be producing more than in order to want to go to a different format?
Yeah, it's a good question. So there's a nuance to it. But I'll give you an example. So the first picture that you saw was an automotive factory. So Tesla spent $150 million in their stamping plant to set up a factory that stamps one car, plus $50 million worth of equipment that goes into that factory that's specific for that car. So like talking about $200 million of investment. So if I want to compare that to our technology, I have to say, with $200 million of investment, how many of these robotic cells can I deploy? Right? So it's roughly, the number is in close to 200. Right? So now with 200 of systems, and it's in the same manufacturing footprint, you get almost the same throughput, but then you're flexible. Now, the more operations we support, that break-even point, to your point, is even goes further up. And the faster the system becomes, the break-even point goes further up. But for a lot of applications, we are already at the breaking point for the traditional technology, right? For example, right now we're working on a defense application that's going to be a few thousand vehicles a month, few thousand vehicles a year. We are already much better, both in terms of throughput and the cost than the traditional technology. So depending on the geometry and design, it can be a few hundred thousand. But once you get to maybe like a few million, then that's where we're right now. The traditional technology is better. But again, as we're improving the speed and the capability that we have, we're closing that gap.
Yeah, for sure.
So I was wondering, how would this apply on, say, eventually a smaller scale, where you could have like a small business have their own sort of production for a smaller piece or part that they do on their own?
It's a good question. It's definitely in our roadmap, but not near term. The focus that we have had so far was on larger products, right? Those are the ones that the tooling is much more challenging. The factory flexibility is much more important. So the current focus is like much larger products. The frame that you see, the envelope that we have is roughly a 15-foot by 5-foot envelope. And that's kind of allows us to do like, class 3 to 5 of like missiles and UAVs. And that's where we saw the main problem was in terms of agility. I think down the road, you're right, it makes sense to maybe go to smaller sizes and support smaller equipment. All right, thank you so much, appreciate it.